Welcome everyone to our segment on electricity. This year we've got a great opportunity. We're meeting with Ward Eshelman at Ward's Electric. Ward, thanks for joining us today.
You are welcome.
Thanks for being here. Ward's going to talk with us today about electrolysis or galvanic corrosion as it's properly referred to, and we'll talk a little later on about grounding as well, the difference in the systems and what makes one specifically different from the other. Ward, one of the things that we talked about before our conversation even began here is you were going to convince me to dispel the use of the word electrolysis. Tell me why that is.
That term is used a lot in the corrosion business, in the marine corrosion business, but it is used probably most of the time improperly. Electrolysis is a chemical phenomena that happens to the electrolyte or the water that a boat is sitting in during current passage through the water. It could be straight current, it could be galvanic current, the type of current doesn't matter, but it is a breakdown chemically of seawater and breaking it down into the two hydrogen and oxygen gases. So it's what happens to the water. It's not what happens to a metal that may corrode, whether it's a metallic hull or a through hull fitting. So really the proper term within our industry or any industry that's involved in corrosion is using that term corrosion. Now there are many different types of corrosion. As you mentioned earlier, we have galvanic corrosion, we have straight current corrosion. Anodic protection, cathodic protection is actually a form of corrosion in and of itself. So I have been on a mission for many years to correct that within the industry. And I have to be honest, we at Ward's Marine Electric many years ago called our corrosion surveys electrolysis surveys, which was incorrect. We changed it many years ago to corrosion surveys.
So I want to back up just really briefly. And you know, we as lay people, the general public, we think of corrosion, we think of rust, we think of pitting in aluminum. That's what we consider to be corrosion, or that's what we would normally think of when we use the term corrosion. Tell me why we're calling this corrosion. What is the actual effect that occurs that we're going to talk about our bonding system, and we're going to try to avoid the existence of the corrosion?
Well, corrosion isn't always necessarily detrimental. You had mentioned rust as being a form of corrosion, which it certainly is. But in essence, rust can become actually a protective coating for steel, iron, those types of metals. So that's a case of corrosion, yes, which can be detrimental, but it also can be protective in nature. Now, most of the corrosion that we see in the marine industry is harmful in nature. And I had mentioned earlier, one form of corrosion is straight current corrosion, where we actually have electrical current leakages on a boat that end up contacting something in contact with seawater. And then causing a corrosion of that metal to another. There has to be an anode in this particular corrosion cell and a cathode. The anode is the metal that is deteriorated or sacrifices into the electrolyte that I mentioned earlier, and then plates out on another piece of metal, which is called the cathode, in a electrochemical corrosion cell.
So when we have any time that we have two dissimilar metals in seawater, we've created what?
That would be a galvanic cell.
Action. Right? So what we've done is we've created a battery, in essence. And
yes.
Is that correct?
That is correct.
So the electrode and the cathode, tell us in 101 terms, what is the electrode and what is the cathode in that environment?
Okay, well, they're both electrodes. One is an anode in a corrosion cell, and that is going to be the less noble metal, higher potential metal. It has to be, in order to have this corrosion, there are four requisites that have to be met. It's not just enough to have the two pieces of metal in contact, even close to each other in seawater. They won't corrode. There has to be an electrical connection between the metals. So there has to be an electrolyte, which in our case is seawater. There has to be an electrical connection, which can be metal to metal contact, or it can be bonding type or grounding type contact. There has to be a potential difference between the metals, which we're talking about. Typically, an anode is going to be a higher potential metal. And a cathode is going to be a lower potential metal. Let's say if we interconnect steel to bronze in seawater, and they're electrically connected with a conductor, and we have a resultant current flow, which is called galvanic current, then we start a corrosive cell, which will be harmful, detrimental to the anode, the steel, and protective in nature to the cathode, the bronze.
Okay. All right. So the one that we're most familiar with in the marine industry when it comes to the nobility of metals, obviously, is zinc. That's the one that we all know. Everybody in the marine industry knows that you got to have zincs on the boat. You got to have them in the engine, you got to have them on the shaft, or you got to have them on the hull, and they've got to be on the bonding system. Let's talk about that bonding system and how zinc plays into that system, and what are we doing with that actually? We connect everything. What does that do?
By connection, and referring to the American Boat Yacht Council electrical standards, there is a standard E2, which is the cathodic protection standard, and bonding has been, the name has been somewhat expanded to cathodic bonding.
Okay.
And the purpose of that bonding is to interconnect the metals that are exposed to seawater. Let's say if we're talking about a fiberglass hull, we would include the running gear, rudders, struts, propeller shafts, through-hole fittings of any type that are metallic in nature, inlets, discharges, bow thrusters, stern thrusters, all these types of equipment. In order to be protected by sacrificial anodes, like zinc, it's one of three major types of anodes, they must be bonded with this cathodic bonding system we're talking about.
Okay.
In order for the protection, the protective current from the sacrificial anode, the zinc, to reach the metals that you want to protect.
So what you're doing is you're drawing that current to the least noble of the metals and letting it be the one that corrodes away or erodes away, and thereby protecting the more noble metals, be they bronze, steel, whatever the case may be, because they're higher on the table of noble metals. Is that a correct interpretation?
Well, they're actually lower, or excuse me. Zinc, if we take the Galvanic series, which
Okay.
it basically is a ranking of all types of metals from least noble to most noble. And
Okay.
when we say higher potential, we'll have zinc is relatively near the top,
Okay.
and the lower potential metals are near the bottom. So there's a pretty good potential. When I mentioned potential, we use in our industry a type of what's called a reference cell connected today to a digital multimeter to measure these potentials.
Okay.
The reference electrode that's widely used in the industry is called a silver-silver chloride reference electrode. So in measuring these the potential of all these metals, they have a inherent potential level when they're open circuit in seawater. And with the Galvanic series, we're going to start again at the top with zinc being relatively high. There are other metals that are higher than that.
Okay.
And down at the bottom are going to be your copper-based alloys that we were talking about, like bronze.
Okay.
So when we interconnect, as we talked about, we have a form of corrosion where we have an anodic and a cathodic set of metals. We have galvanic corrosion.
Okay. All right. So in practical application, brokers out at the shipyard, Malcolm Elliott's underneath the boat. He's done banging on things with his hammer. He reaches over into his bag and he pulls out his multimeter. And he puts one of the leads on the prop nut. At first he scrapes a little bit of the anti-fouling off of there, or some of the prop speed, and the owner is shirking and cringing, and the yard is rubbing their hands together because we got to put more prop speed on there. But he gets to a good positive connection with the metal itself, and then he goes with the other lead to the zinc, or the stud on the zinc on the back of the boat. What is it that he's testing, and why is he testing that?
It's testing for resistance between these two separate metals.
Okay.
And if they are bonded together, then that resistance should be very low. And again, according to ABYC standards, any bonding system, you would like to see less than 1 ohm of electrical resistance between anything that's included within the cathodic bonding system. So that's what he is testing and measuring for, resistance in ohms.
Okay, and when we say bonded, we mean connected. Basically, that there is a positive and solid connection between those two pieces of metal through the system, and there is a sacrificial anode attached to it that's going to be the one that goes away.
Correct, and that the resistance has to be very low because the current that's generated between the zinc anode and the metal, whatever metal it is protecting, is a very low level current. So it doesn't take much electrical resistance to block that current, which would render the anode, sacrificial anode, ineffective at protecting the metals. So the resistance needs to be very low.
Okay, all right. Is there any other way to protect the system besides having a zinc on it?
There are other methods.
Okay.
When we've been talking about zinc anodes, they are sacrificial in nature. They're not controlled in any way. It's the inherent current flow between the zinc anode and the metals it's protecting. There are systems called impressed current cathodic protection systems, where you have anodes that do not corrode. It's usually platinized titanium, and you force platinized titanium.
Sounds expensive.
It is. But impressed current systems, one of the major advantages is you have very precise control over the amount of cathodic current that's being produced.
Okay.
So you can preset a potential level, an exact level, and that control system will control the current that's being used to cathodically protect the other metals at a precise point. Whereas with a sacrificial anode system, you really don't have a lot of control. Normally you're going to put on enough anode material, whether it be zinc anodes or aluminum anodes or magnesium anodes, that you really end up probably having a higher protective level than you need. And then as the anodes are depleted, which is what they're supposed to do, they're supposed to corrode, you're absolutely correct, to protect the other metals that are comprised in the bonding system. Whereas with an impressed current cathodic protection system, number one, you have very precise control over the potential. Go back to the sacrificial anode system again. I'm going to use some numbers here just to give you an idea of what happens.
Please.
Let's say a typical fiberglass hull with bronze and stainless steel underwater metals that are bonded. That mixed potential unprotected is probably in the area of 300 or 400 millivolts to silver chloride, as I mentioned earlier.
Okay.
To cathodically protect those metals, we want to raise that potential by at least 200 millivolts. So that takes us up to the area of 600 millivolts for a minimum level of protection. Well, if you put enough sacrificial zinc on a boat to hit 600 exactly in a short period of time, as the anodes deplete and you lose surface area,
You're going to 500, you're going to 450, and you're
exactly.
going pretty soon
So
to 4.
normally, we see it in our corrosion survey work all the time, most fiberglass boats probably are at a potential level of 800 or 900 millivolts, which with time, as the anodes deplete, that potential will start reducing down closer to the 600 millivolt point. And that's the point where you really need to renew, either clean or renew the sacrificial anodes.
Okay. And those systems have been around for quite some time, haven't they?
Yes.
Okay.
Yes.
And you said, is that the only other way to protect other than sacrificial anodes?
Well, another important part of the protective scheme are coating systems.
Okay.
Very important. And usually not always with sacrificial anode systems or any kind of cathodic protection system, it's based upon a reasonable coating system of metals.
Okay.
And protecting uncoated metal is going to take a lot more protective current and therefore consume anodes a lot faster than one with a coating system. Now, coating systems are never perfect. You would like to get there, but you don't typically get there. But so really with a protective system like that, you're taking care of the breakdowns in the coating system. Extreme example, if you had a steel hull that was uncoated and had to install sacrificial anode weight, mass, size to protect that versus one that had a good coating system, big difference in the amount of sacrificial anode mass that you have to use.
You'd have
big
to have
difference.
a lot more.
Yes.
Okay. All right. So we've got a bonding system that connects all these metals that we want to protect from corrosion. And we use one of 3 different systems to do that, or generally used 3 different systems. This is an isolated and closed system per se, isn't it?
Yes.
Okay, all right. So we're only talking about one specific incident. Now, electricity is kind of black magic to a lot of people, myself included. I know to turn the power off before I change a circuit breaker, but I'm not really well versed in it as most of our audience probably isn't. So we have a bonding system, and is it different from a grounding system? How does it differ from how we ground? Is ground the same with AC and DC? Because virtually every boat out there that we're dealing with for our audience, has a bonding system, it has a DC system, and it has an AC system. How do these captive systems differ?
They're similar in many ways, but if we go back to the ABYC standards again, ground on board a boat on a non-metallic hull is described as the main engine or main engines or their bus. In other words, the engine blocks.
Okay.
That's the heart, that is the main point of the grounding system on board a boat. Now, ground is actually, if we talk about shore-based ground, it's earth.
Right.
Earth is ground.
To earth. Right.
Now, in the marine environment, with a boat that's in the water, in seawater, for our case, for our purposes here, ground is really the water that the boat is sitting in.
Okay.
That's ground. But the ground point on board the boat is going to be the main engine, negative terminal, or its bus electrically. Okay. Now, ultimately, both a grounding system, which basically is used with AC and DC systems to interconnect the non-current carrying parts of all the electrical equipment on the boat. The enclosures of electrical control boards, panel boards.
Okay, the non-current carrying components.
Meaning, or motor frames.
Right.
Pump frames, all those types
Housings,
of things.
Sure.
So it's there in AC applications, 120, 240 volts AC, it's there largely for shock hazard protection to people.
Okay.
Main reason behind it. DC, which poses much less of a shock hazard.
Yeah, we don't lose too many guys to DC, do we?
No.
Okay.
AC, because of the much higher voltage that you're dealing with.
Right.
DC, we have grounded systems. You're right, like a 12-volt DC system or a 24-volt DC system, and in the old days, 32-volt DC systems, which we don't see very much anymore,
right?
are usually the negative side of that system. The DC system is intentionally grounded.
Okay.
And the same thing for 12 and 24-volt systems. So, and then ultimately, in theory, you would like to have one point on the boat where the AC, DC, grounding, and the cathodic bonding system connect to.
Okay.
From an electroengineering design standpoint, that's what you want to have. In the real world, you end up with a lot of what are called parallel paths to the ground. But again, cathodic bonding is there to interconnect the metals that you want to protect with a bonding, with a cathodic protection system, whether it be sacrificial in nature or impressed current, like we talked about earlier. So there are things that are one and the same for these systems, but they all do different things for different purposes.
Okay. So we have a DC ground and an AC ground will be completely separate, though. You wouldn't ground AC to your engine block, would you?
Yes, you do.
You would? Okay.
Oh, yes.
So you can use the same earth or ground for either AC or DC.
Correct.
Okay, and how do you, is there any worry or concern of that ground feeding back the other way from one system into the other if you're using a common ground place?
No, because again, a grounding system, which will include bonding, is normally not carrying current until something goes wrong.
Okay.
You have an electrical fault. You have a short circuit. If it's a 120 volt appliance or a 240 volt appliance, and you have what's called a ground fault of a live or energized section to ground, that current is carried back to the ground point, and the power sources have grounding of what's called a neutral conductor, and you'll end up tripping a circuit breaker or blowing a fuse in those situations. So for safety purposes. So there's no problem with backfeed. There is a unique problem with shore power systems, since we're talking about AC systems on boats.
Okay.
Shore power systems, which a lot of boats have today, you look at the changes through the years,
Oh, absolutely.
There are boats today
we used to have those nice light little 30 amp cords. That was all we had.
Right.
Now it's 100 amp cords and bigger.
It's amazing how much this has progressed, but we have a unique corrosion problem in our industry. When a shore power cord is connected between the boat and the dock, there is a grounding conductor in that shore power cord.
Right.
If it's a 120, 240 volt single phase cord, it will have 4 conductors in it, 4 wires. Line 1, line 2, neutral, and ground.
Okay. Line 1 is 125 volts, line 2 is 125 volts, so that gives you your 250 volts.
Exactly.
And then you have your neutral and a ground.
And the grounding conductor by design, interconnects the boat's ground, which again, the main point on a non-metallic boat is going to be the engine or engines, propulsion engines, back to the dock ground, or essentially earth.
Okay.
So it sets up a galvanic corrosion cell, which typically the boat is at a higher potential than earth or the dock ground. So what happens now, you have a path for the protective current from the sacrificial anodes are not only trying to protect the metals on that particular boat, that protective current is lost back to the dock.
So it's doing a bigger job than it was designed to do.
Exactly.
So in the design phase, how do we accommodate for that? Because knowing that, let's just use as an example a 60-foot motor yacht, and you're charged with designing the electrical system in that boat. How do you accommodate for the fact that that boat's going to spend, let's say, 250 hours a year underway on its generator and independent of shore power, and it's going to spend all the rest of that time connected to Earth? How do you accommodate for that?
There is an electrical device called a galvanic isolator.
Okay.
Which was developed actually a fair number of years ago. And it effectively it's installed in the grounding conductor circuit on board the boat. It's not at the dock, it's at the boat. So anywhere that boat goes, it receives
brings that protection with it.
And effectively what it does is it blocks that low-level DC or current that I'm talking about that causes the anodes to work harder and therefore sacrifice faster. It blocks that low-level, it's actually a DC voltage that's created there. And not in terms exactly of like a 12-volt DC system, but just the potential difference that I talked about earlier. It blocks that galvanic current flow, but it maintains the integrity. Again, the main reason for the grounding conductor in AC systems is for shock hazard protection to people on or near the boat.
Okay.
So you don't want to disturb the integrity of that, so it looks like a short circuit to alternating current, meaning when I say it passes right through the device. It's not impacted by that at all, but it blocks this low-level DC voltage and resulting current that can cause accelerated anode deterioration and greatly accelerated at times. So it's a device that typically, on an OEM basis, the builders are installing. In the aftermarket, we install a number of them too, but it's a simple device. It really is passive, and it does probably one of the greatest services, because years ago, this was a big problem in the industry.
Yes.
Big problem.
Yes.
And because if you lose the anode area down to a point where your metals aren't protected, then they're going to start corroding.
Your short cord is going to cause your boat components to start corroding.
Yes.
So is a galvanic isolator something that requires any maintenance, any renewal over a period of time, any inspections? Is there anything about a galvanic isolator that the audience could know that maybe they didn't know before they tuned into this?
The tests should be performed on some type of periodic basis, because one of the major components within a galvanic isolator are diodes. They're solid state components. There are typically 4 of them. They could be impacted by lightning strikes, and I'm not even talking about a strike that hits the boat or the dock. This could be some distance away that could
even a
compromise.
Power surge. If you go to a third world country where you don't have stable, clean power, that power surge could create an issue with the diode. Correct.
Correct. And you can't just visually look at a diode and tell whether it's functional or not. There are tests that could be performed, which are really quite simple. So that's something that's important, because you can't visually look at a galvanic isolator externally or internally and tell if it's working. There are tests that can be performed simply with a digital multimeter that can prove that the components are indeed good.
Okay. And is that something that you would recommend people do on a periodic basis, maybe annually, or after you've made your summer season trips to foreign ports or places that you aren't 100% sure, or you were away from the boat, it's summertime, thunderstorms virtually every afternoon, a lightning strike occurs, a distance away from the boat, but could create a power surge and affect your galvanic isolator on your boat then?
Yes.
So, okay.
It's important to do, yet I have to be honest, I doubt that a lot of people within the industry, boat owners or boat operators, really do that. It's a part of
our... With any luck at all, a couple of them will do.
Hopefully so. Or find a qualified technician to do it. Again, it's not a difficult test. It's a standard part of our corrosion survey that we do for boats. but it's a qualified marine technician or electrical technician can perform the test.
If I were to ask you to thumb back through your historical records and from when we used to do electrolysis surveys now and we do galvanic corrosion surveys, what would you say is probably the #1 issue that you've run across in compromised integrity of these systems?
Probably going back to what we just talked about, the galvanic isolator, grounding a boat back to the dock. And today, if you look at just take the large center console vessel industry, how much these really big boats with at least dual, triple, quad outboard motors in seawater with shore power always, if the galvanic isolator is #1, or if it's not installed, or if it's installed and it's defective, or sometimes we've seen them installed not correctly electrically, it can cause the aluminum, the outboard engines, aluminum corrodes very easily if it's not protected. And we've seen a lot of damage to outboard engines because of either galvanic isolators not being installed, defective, or improperly installed, bypassing the isolator. That's probably one of the most common problems.
So integrity of the system by bonding wires, the ends corroding off of them because they lay in a bilge with a little bit of seawater, and that's probably been one of the #1s. But that's a very interesting point that you bring. And today, the galvanic isolators are there to perform a very specific function, but they're kind of out of sight, out of mind, and people don't think about testing them and checking them.
And it's true, going back what you were talking about with cathodic bonding systems, these systems being in bilge areas are a very tough environment.
Right.
So you're right, corrosion of terminations and connections can cause, remember we talked earlier about it doesn't take much resistance to block that protective current flow from anodes. So corrosion to terminations where you have a bonding conductor connected to a through-hole fitting or a piece of running gear with a ring terminal, and if that becomes corroded at the interface, there could be enough resistance to block the protective current flow. And typically, nothing is found out until you start experiencing corrosion problems.
Until your propellers turn nice and pink.
There you go.
Yeah, and the bonding system is much like a tree in the respect that you've got a trunk or a main line, but you'll have branches, and then you'll have some small branches off of that sometimes as well. So every component isn't interconnected into the main line directly. It can come through another connection or a series of connections into that bonding system, into that closed loop, if you will.
Yes, and it's in installing cathodic bonding systems, it's always best, as you mentioned, having a main conductor running through the boat and actually connecting to what are called bus bars in a major compartment or area, say within fixed bulkheads. And rather than what we might call daisy chaining, where you're connecting bonding from one fitting to the next, if you have a failure of a connection at the beginning of that point,
the whole system,
everything downstream from that is lost. So it's best electrical practice is to install a main bonding conductor through the boat, have bonding bus bars in each major compartment, then go out with individual conductors to each through-hull fitting or piece of running gear you want to protect. Best system.
And is that always the green wires?
Yes.
Okay. All right. I think I've learned a lot about bonding that I didn't know before. I thought I had a pretty good understanding of it. I now know it's not electrolysis. It's galvanic corrosion. So that's a win for both of us. Ward, thanks very much for your time. Your expertise is unbounded, no doubt about it. I really look forward to future yacht engineering seminars where we can dig into other parts of the electrical system. We're going to learn a lot more from you. Thanks very much, everybody, for joining us. I hope you enjoyed that segment. We're going to cut to a commercial break.
Yacht Engineering Week 2021 has been made possible by Pantropic Power, the only authorized Caterpillar Power Systems dealer in South Florida. Florida Nautical Surveyors, your complete solution to all of your vessel surveying needs. And Robert Allen Law, exclusively dealing with the business of yachting. We would also like to thank Quantum Stabilizers, AME Solutions, DeAngelo Exhaust, MPI Marine Professionals Incorporated, Concord Marine Electronics, Lauderdale Marine Center, Marine Data, Isotropic, Dockmate, and Murray Ventilation Products. Thank you for joining us this year. We'll see you in 2022.